Hi, everyone. In today's lesson, we are talking about bias and misleading statistics. As usual, follow along with the video lesson. I provided a PDF lesson sheet, not a ton of math necessarily to do today, just some discussions to be had or just things to ponder and think about. So let's begin. So first, we're going to talk about the four main types of bias. This information I have provided on the lesson sheet, just a lot of writing. So I think I just saved you the effort there. The first type is response bias. Response bias is when respondents change their answers to influence the results to avoid embarrassment or to get the answer they think the questioner wants. So a typical example might be, somebody asking you if you've ever drank before or done drugs or something controversial. Depending on who's asking you, you might not saying those things are good or bad, but you just might not feel comfortable answering. You might just give the answer they think they want. Here's an example that you guys have. A teacher asks students to raise their hand if they cheated on last week's test. Even if you did, it's not likely that you're going to want to admit to that. So the teacher's not going to get accurate results. If 5 and 30 people cheated, 0 and 30 are probably going to raise their hands. These kind of things can come when questions are uncomfortable too, like even a survey asking people sensitive issues like their weight or whatever you might find sensitive. People might take a few years off, take a few pounds off, that kind of thing. The second significant type of bias is called measurement bias. This is when the collection method is such that the characteristics are consistently over or underrepresented. So I worked in a meat department when I was in high school, and sometimes little old grannies would ask me if I had my thumb on the scale as I was weighing their meat, meaning I was putting my thumb on and changing the measurement and making it heavier, making the actual the mass of whatever I was portioning out was more, and they'd be getting charged more. Of course, I would never do that. But that would be an example of measurement bias. If you had a scale that's not working properly, if it's maybe always giving the bigger weight or always giving a smaller weight. In the same way you want your scales to work and give you accurate measurements, you want your collection methods to give you accurate measurements, or as accurate as possible. So a typical example, example of this would be this survey question. So a lot of people do not like math. How would you feel being referred to as a math geek? So this is one type of example of measurement bias, a leading question where the wording can affect the outcome, influencing someone's answer. Other types of measurement bias can occur when the collection method affects the results, like when in a multiple choice question, the options are too limited for an honest response. So for example, I think I gave this example for, the White House a couple of years ago had a survey. Just imagine if you had this and imagine you had these three options. Is the president doing a good job? Or what kind of job do you think the president is doing? And you had amazing, and you had great, and you had pretty good. So obviously, and you were forced to pick one, let's say. You couldn't move past this survey page until you answered the question. Obviously, these are limited response, and you wouldn't get, it's not an honest question, right? So that's a couple examples of measurement bias. The next is sampling bias, when the sample does not closely represent the population. So if I was, concerned about if I wanted to get information on people on maybe graduating students and how people are feeling, if there's any anxiety, say leaving high school, I'd probably go ask the grade 12s or people pretty close to graduating. If I went and asked a grade 9 student, what are your feelings towards leaving high school? They probably haven't worked through those emotions yet, right? That sample would not represent the population, which would be graduating students. So have an example here. A politician goes back to the farming community she grew up on, asked her opinions on her latest initiative for the agriculture industry. So it's likely a larger proportion of these people would support the initiative because she grew up in a farming community, right? So to get a better idea of her constituents, she would want to visit not just like a rural farming community, but the suburbs and cities. She'd want a good idea of the whole province, riding, whatever it is, right? And the last is non-response bias. This is when the opinions of respondents differ in meaningful ways from those of non-respondents. So a typical example would be, I'm not sure if they have these anymore, but like at McDonald's, you could have a little card where you could fill in how your service was. Most people who go to McDonald's kind of get what they expect to get, have their food, and then go on their way. It's not everybody, right? Your average Joe customer is filling in these. The people that really fill those in is when something negative happens. And so if you were basing if you were thinking, well, how is my franchise doing? And I'm going to base my opinion on all of the cards I get from customers. Well, if they're mainly negative, then you might think that you might be doing a terrible job. But the fact is only the people, and there might be only a few people that have negative experiences are actually filling those out. An example here, a mail-in survey asked respondents about their drinking habits. Only 3% of surveys were returned. Such a small return would likely not yield a representative sample. 3%, it's not a lot of population, or it's not a lot of the percentage. It's only 3 in 100 surveys mailed back. And those who responded often had very strong opinions about the subject matter. And so the results could easily underestimate the feelings of the population. So that is the difficulty with mail-in surveys, call-in, where people have to voluntarily give information. All right, so as a little exercise here, just follow along. I'm going to throw up a scenario to you, and you think about why it's biased. So here, a parent council survey is conducted to learn if an after-school music program should be offered. So here's the survey question. Early musical training helps develop brain areas involved in language and reasoning. Should the school offer an after-school music program? So if you want to pause and think about it, you can unpause when you're ready. So this is a leading question or a loaded question. It definitely is trying to influence the person being surveyed. That initial sentence, early musical training helps develop brain areas involved in language and reasoning. It makes it pretty hard to say no to an after-school music program. So it's definitely a leading question. To make it a fair question and not biased, probably just should ask, should the school offer an after-school music program? So this was an example of measurement bias. Next one, a group of 30 to 40-year-old women are taking part in a psychology experiment. So to save paper, the researcher gets them to state their physical attributes, their age, their mass, their height, in front of the group instead of filling out a form. Think about what type of bias this is. If you said response bias, you'd be right. These are sensitive questions, and they're not exact. They're not keeping things anonymous. Maybe if you were writing these down anonymously, so people wouldn't know. But yeah, if other people are going to hear you say your weight, your age, that could definitely get awkward and lead to some people not telling the truth or just refusing to respond. Why is this one biased? So Mr. Smith's mom wants to find out which Dancing with the Stars celebrity is most popular. So she goes to a local hockey game to pass out surveys. So which type of bias would this be? If you said sampling bias, good for you. So hockey fans, which are the sample, might not represent the population, which would be Dancing with the Stars fans. Now, there could be people that overlap, and I'm sure there are, but likely not a good sample in that case. And here's one more. So at a new restaurant, waitstaff ask every 5th customer to answer a questionnaire about food quality and service once they finish their meal. And about 30% of customers surveyed actually filled out the questionnaire. And the majority of those complain about poor service. So the manager concludes the waitstaff needs more training. So every fifth customer and only 30% of those customers filled out the questionnaire. So if you said non-response bias, good for you. So, again, people that fill out these questionnaires generally have strong opinions. In the case of restaurants, usually it's negative ones. All right, so those are the 4 types of bias you should be familiar with. You should be able to identify them, and maybe, in the case of a survey question that's biased, maybe tweak it to make it unbiased. We're going to talk now about some misleading statistics. So we're going to just run through 5 scenarios together. I'll put up the scenario and let you think about why this may be misleading, and we'll just have a little discussion about it afterwards. So let's look at this first one. So the Daily Mirror and the Times retweeted this tweet about a British high-speed rail project that is expected to take 20 years to complete. So the tweet was, interesting stat, 93% of today's UK population will be dead by the time HS2 is finished. Wow. So the reason this is misleading is because it's just like factually untrue. Like, you can't have 93% of a country's population dying within 20 years. Like, that's obviously not true. These newspapers didn't actually verify the number was accurate before retweeting. So this is like secondary data for sure, right? These people didn't collect this statistic themselves. They just trusted that this original tweet was true. And this is especially true for today with Facebook and this whole idea of fake news. Is this, you just can't believe everything that you hear. You have to delve deeper because our own media outlets don't always get it right. And everybody's race to be first to reporting things, this can happen quite a bit. So don't believe everything you read. Like, don't not believe everything you read either, but just like be aware, right? So our second scenario, in 2005, the British Cheese Board conducted a study to show that eating cheese does not give you nightmares, because I'm sure the British Cheese Board, wants people to keep eating cheese. Let's talk about why this may be misleading. And if you would like to pause the video and think on it some more, be sure to do that. If I asked you to quantify nightmares, how would you quantify nightmares? Would you have a scale of rating, how scary your nightmares are from 1 to 10? Or would you say on average, how many nightmares you'd have per week? How did the study do this? In a case like this, where you're trying to disprove something, like that cheese doesn't give you nightmares, you want to study the validity of the data and how they collected their data, really closely. Because how can you quantify this idea of nightmares? So when you hear these, I read, you might see on Facebook, somebody saying this study showed this study showed that. Well, what was the study? Again, you can't believe everything you hear, especially if it just says, this study showed this. Third scenario. So here is a circle graph showing the distribution of eye color among classmates. And as you're thinking about this, I might preface with saying, if the percentages weren't there, how might you feel about this circle graph? So if you looked at the 11% and 13% bars, if you didn't have those percentages, and not all circle graphs do, would you be able to tell which one is bigger, whether there is more hazel eyes than green eyes? I certainly couldn't. In this case, a bar graph would have been a better choice, because then you could do an easier comparison between all the different eye colors. So it's not that this is a bad idea, just oftentimes when you see something, a graph or a statistic that's misleading or kind of unclear, it's not always intentional. It's not always with evil intent. This is a perfectly fine circle graph, just maybe a bar graph would have been better. For D, let's look at this scenario. A newscaster reports about a survey that asked, did scientists falsify research to support their own theories on climate change? And this was in an actual newscast. And you've got the following, you see the summary there. 59% somewhat likely, 35% very likely, 26% not very likely. So see if you can figure out what's misleading about that. And then unpause when you're ready. So if you noticed that the percentages, if you add them up, those percentages don't add to 100%. So something's fishy here. Something's very fishy. This newscast was reporting about a survey. So they actually took the survey results and made their own kind of condensed version of it, showing either what they wanted to try to skew the data and make it look a certain way, which definitely happens, or unintentionally. Don't know what happened here, but here's what the original survey looked like. So you can see that the 59% came from combining the top two guys, 35% and 24%. And then 35% very likely shows up. So you can see they actually counted that twice, right? And then 26% not very likely combined these two guys. And they didn't even include the 15%. So that was like skewing the data even more. There's like a double, there's like two things bad going on here. So yeah, I mean, again, you can't always, when a newscast is reporting a survey and creating their own graphics, you have to be aware whether they're creating a graphic to suit their own needs. Here it was you can kind of see that the percentages don't add up. Our last one. So research shows that if you eat a sausage a day, your risk of a certain type of cancer goes up by 20%. So let's talk about why this may be misleading. The reason this may be misleading is we need to actually have a bit more information. Is that 20% increase significant? If 5 in 100 people have this type of cancer, then what an increase of 20% means? Well, 20% of 5 is 1. So an increase of 20% just means that instead of 5 in 100 people having this type of cancer, 6 in 100 will have it. Now, that bump of 1 may be significant to you. It may not be significant to you. But the thing is, without this kind of information, without more detail, it's not clear whether it's significant or not. For example, if a certain disease affects only like 1 in 10 million people, if 2 in 10 million people have the disease, then you could write a headline saying that we've had a 100% increase in this disease, but it's actually just like only one more person out of so many, right? So you need more. Sometimes when you have stats like these and percentages, you need to know just more details. So yeah, I'm not saying an increase of 1 is not significant, but you just have to have more information. Talking about significance, when you see large numbers, especially right now with all the COVID-19 and governments announcing billions and trillions of dollars in aid, and millions for smaller municipalities and whatnot, it can be overwhelmed. You might think, wow, those are really big numbers. But then when you actually break it down, it's not so big. So you just have to do a bit of thinking. So here's, we got to try to put things into perspective when we see big numbers to see if they actually are really big or they're not that big. So here's our first example. We'll actually do some number crunching with these two. So a recent settlement of 52.5 million was awarded to 970,000 households from Quebec after a really big ice storm in 1998. So that sounds really big, right? Like, Quebec is really paying out a huge amount to households. But let's actually see how much that is per household. So the dollars per household. So 52.5 million is 52,500,000. And we're giving that to 970,000 households. And those numbers will fit just fine on a calculator. So just do that really quick. 3 divided by 970,000. So that is a grand total of about $54 per household. So 52 million sounds like a lot, but it was only $54 for a household. And if you can imagine a huge ice storm going through, maybe damaging some of your home somewhat, maybe a bit of the roof got damaged, maybe you had some trees that fell over due to the weight of the ice and maybe landed on your shed or damaged your vehicle. $54 simply wouldn't handle that. So it's actually not that really not that big. So in this case, that large number wasn't so large after all. Let's look at a second example here. So Switzerland has the highest consumption of chocolate per person in the world. The population is 8 million people, and they eat about 82 million kilograms of chocolate each year. So 82 million kilograms, that's a big number, 82 million. But, when we look at the specific details, is that actually a lot of chocolate per person? Let's actually find it. Let's actually just do some calculations here. So 82 million kilograms for 8 million people. So let's find out, well, how much is that per person, first of all? So we'll do a little calculation there. So 82 million divided by 8 million. The millions are kind of irrelevant. So you can just do 82 divided by 8. I think it's 10.25, but I'll just verify it here. Yep. So that's 10.25. So 82 million kilograms per 8 million people. So that's 10.25 kilograms per person in a year, right? That's just in 1 year. So if you can visualize 10 kilograms, that's about 20 pounds, 22 pounds. It seems like a lot. If you had that all sitting in front of you, maybe you had that much after Easter, I don't know. It definitely is a large volume of chocolate, certainly to take in a day or a week. But for a whole year, I'm not sure if that's a lot for a whole year. So let's actually look about how much is that per week, let's say. So let's take 10.25 divided by 52 weeks in a year. So 10.25 divided by 52. Let's just call that's about 0.2 kilograms or 200 grams. It was really about 197 grams, but let's just round it up. So that's about 200 grams of chocolate per week, right? And if you think of maybe, say, the average candy bar being just going to rough it here, maybe 50 grams, that's four bars per week, 4 chocolate bars per week. So now that we've got more information, we've taken that large number, we've kind of parsed it down into something we can kind of wrap our minds around. Maybe 4 bars a week is a lot of chocolate for you. Maybe you don't eat a lot of chocolate, but maybe you have a bar of chocolate every day, that's your treat or something, right? And so for you, maybe that's not a lot. But now that we've taken that big number and broken it down somewhat, whether you think that's significant or not, you can actually make now a more educated decision. All right, and the last thing to talk about, and that's especially relevant these days as infographics are actually becoming more and more popular. They're actually pretty cool. One of the days where we just you just have if some news outlet or magazine wants to display some information, a circle graph and bar graph, they might be fine and dandy, but sometimes they want to have something that looks visually appealing. It catches the eye and draws people to their product, right? So infographics can do that. They combine both visual and text-based representations of data. So this is an infographic that was posted in the New York Times in 2006. And I purposely don't have any of the headlines or anything. What do you think what story do you think is being told through this infographic? So if you want to pause the video and just like look at it a bit more, you can unpause it when you're ready to discuss. But this type of infographic is called a heat map. So instead of using like red and blue, they've used really dark squares for the most common birthday, really light squares for the less common. And I know it's hard to tell, but every single one of these squares actually has a different is a different color. The darkest ones are the most common birthday, and the lighter ones are the least common birthday. And what this graph actually tells you is that more people are born in July, August, September, and actually September is the month with the most birthdays. So birthdays aren't actually spread out throughout the year evenly. There's actually more people that have birthdays in September, which is actually kind of cool. But the thing with infographics is you do have to. They're not always like cut and dry. You have to kind of work to get information out of them. And I guess you have to be really careful creating an infographic to make sure that you're not skewing any data. But I thought this was a cool one to share with you guys. So your next steps, I've given you guys some practice. It's much like the lesson here. There wasn't a lot of like calculations, identifying types of bias, thinking about how you might reword a question, thinking about whether a statistic is misleading, and also interpreting an infographic or two, just looking at an infographic and answering some questions about it. The key things for you guys to be able to do after today is know your 4 types of bias, be able to recognize if a statistic is being misleading or not. If I gave you a really large number in a statistic, could you pare it down into something that we can wrap our minds around and see if it's significant or not? And also be able to interpret an infographic. So that's it for today, guys. Hope you're doing well. We'll see you soon.